In this lecture, I will explain how to obtain RE transistor model. In the last few lectures, we have completed H parameter model, and both H parameter and RE transistor models are used for low frequency signals. So we can categorize the transistor models for small signal analysis based on frequency. For low frequency, we have H parameter model. We also use RE model in case of low frequency signal. For high frequency, we have hybrid pi model. And we also use Y parameter model for high frequency. In this course, we only have to learn H parameter model, RE model, and hybrid pi model. We have already completed H parameter model or hybrid model, and in this lecture I will explain how to obtain RE model. We will find out RE model for common emitter transistor. We will find out RE model for common emitter transistor. In case of common emitter configuration, the emitter is common to the input side and also to the output side. So we will make emitter common to the input and output sides. We are considering NPN transistor, but you can also take PNP transistor. Everything will remain same, only the direction of currents will change. This is base terminal. I will represent the base terminal by small b. This is collector terminal represented by small c, and this is emitter terminal represented by small e. The input current is the base current represented by small I subscript small b. The output current is the collector current, and this current is the emitter current. The input voltage is VBE, and the output voltage is equal to VCE. Instead of having the transistor symbol, we will have the transistor itself. It will help us visualize things more clearly. You can see I have removed the transistor symbol, and we can consider the transistor as two diodes connected back to back. So I will make two diodes connected back to back, in which this diode is reverse biased and this diode is forward biased. So I will modify this circuit in which collector branch will have the dependent current source and the emitter branch will have the forward bias diode. We have dependent current source because current is equal to IC, and IC is equal to beta times the base current. So collector current is dependent on the base current. So we have the symbol of dependent current source with current IC equal to beta times the current IB, and here we are neglecting the reverse saturation current because collector current is equal to beta times IB plus beta plus 1 times reverse saturation current. If you see the output characteristics of the common emitter transistor, you will find the output resistance is very large because resistance, or we can say output resistance, is equal to 1 by slope of the curve, and you can see slope is nearly equal to 0. This implies the output resistance is nearly equal to the infinity. So we have output resistance here and it is equal to infinity. Resistance RO is equal to infinity. So we can also neglect the output resistance because it will remain open circuited, because no current will flow through resistance RO as it is equal to infinite. Now we will talk about the forward bias diode. If you see the input characteristics, you will find it is similar to the forward bias diode characteristics. If you remember the diode chapter, we have studied three types of diode resistances. The first resistance is DC resistance. The second resistance is AC resistance. AC resistance is also called as dynamic resistance. And the last resistance is average AC resistance. We will consider the second type of resistance because we are doing the AC analysis. We will consider the AC resistance or dynamic resistance. It is represented by R subscript small d, and it is equal to delta VBE by delta IB. VBE is the input voltage and IB is the input current. So we can further improve our model by replacing the diode with the dynamic resistance RD. Diode is in the ammeter branch, and after replacing the diode with resistance RD, it will go to the ammeter branch and current IE will flow through the resistance. So we will change the representation. We will change the representation of resistance RD, the dynamic resistance, and we will represent it as R subscript E, where E represents the ammeter. So we have resistance RE in place of diode, and this is the complete RE model of the transistor. Only one thing is left, and it is the calculation of resistance RE. So we will find out resistance RE. I will consider PN junction diode in which the diode current is equal to ID. The diode current is equal to ID, and the reverse saturation current is equal to IS, and from diode current equation we have ID equal to IS inside the bracket VD divided by eta VT minus 1, and I will differentiate this equation with respect to VD. So we have dID dVD equal to IS is constant because it is reverse saturation current, so we have to differentiate e raised to power Vd divided by eta Vt minus 1. We will differentiate this quantity, and let's say eta is equal to 1. Eta is equal to 1 for germanium and eta is equal to 2 for silicon in case of low diode current, but when diode current is high, eta is equal to 1. So eta is equal to 1, and let's say we are performing this calculation at room temperature. So temperature is equal to 300 Kelvin. After differentiation we have 1 by RD, because dVd by dID is equal to RD. On the right hand side we have IS e raised to power Vd by Vt divided by Vt. This is what we have, and from here you can see IS e Vd by Vt when eta is equal to 1 is equal to ID plus IS. So we have 1 by RD equal to ID plus IS divided by Vt, or we can say 1 by RD is equal to ID, because IS is very small as compared to ID, so we can neglect the reverse saturation current. So finally we have 1 by RD equal to ID by Vt, or we can say RD is equal to Vt by ID, and at room temperature Vt, the volts equivalent of temperature, is equal to 26 millivolts. So resistance RD is equal to 26 millivolts divided by the diode current ID. Now by using this we can easily find out resistance Re. The only thing we have to do is to change the representations. Rd is resistance Re equal to 26 millivolts divided by the diode current in case of common ammeter configuration is the ammeter current. So by using this formula we can easily calculate the dynamic ammeter resistance, and for this purpose we need to draw the DC equivalent circuit, because current IE is the DC part of the ammeter current. To calculate current IE we need to draw the DC equivalent circuit, and we can easily calculate the ammeter current from the DC equivalent circuit. We have already solved various examples in which we have calculated different parameters of DC equivalent circuit. So this is all you need to know about the RE model of the common emitter transistor. This model is also called as T model, and in this model RE is equal to 26 millivolts divided by emitter current IE. In the next lecture we will perform few simplifications. In this circuit you can see input and output sides are not properly separated, so we will try to separate input and output sides, and we will also discuss the output resistance. Now we will move to the next part of this lecture, in which we will find out RE model for common base configuration. For common base configuration, in case of common base configuration, base is common to the input side and also to the output side. Now we will find out RE model. I will convert this to homework problem. This is the homework problem, and in this problem you need to match the correct options. In column number 1 we have resistance RE as the first element, and the second element is the current dependent source. The current dependent source having the current IC, which is equal to alpha times the current IE. These are the two elements in column number 1. In column number 2, first element is position 1 and the second element is position 2. Position 1 is this position and position 2 is this position. So match the correct options, and once you have your answer, post it in comment section. I will end this lecture here. See you in the next one.